Let's go through the questions for chapter 15.2. Question 6. An object attached to one end of a spring makes 25 complete oscillations in 5 seconds. What are its period and frequency? In order to answer this question, you need to know the definition of frequency and its period. And you will answer this question with ease. So we used to define frequency as the number of waves that passes per second. Okay, so in this case, you can define your frequency as the number of oscillations that passes in 1 second. Okay, so using this definition that you already know for frequency, okay, you will derive a formula. You're not really deriving, but the definition itself is telling you the formula, okay, in which in this case you will say 25 divided by 5, getting 5 seconds, 5 hertz, okay, getting 5 hertz of frequency, okay. And then for period, we already know the formula for period is 1 over the frequency, okay. So we're already going to use 1 over 5, which is going to give us 0.2 seconds. So this question is simple. We just have to use the definition of frequency and the period. Using what you are given, you'll get the answer. Okay, coming to this question, what is the period of the motion represented by the curve? So once again, we have to use the definition for the period. And how do you define the period? Period is the time for one oscillation, okay? So this is how I'm going to analyze this graph. So now I'm looking for one oscillation. You can see on the y-axis we just have position, and then we have time on the x-axis. So what I'm going to do, if you look at where this graph starts, it starts at x equals to 2. So I have to look for the time at which this graph repeats itself. Okay, this is the definition of period. So I'm going to draw a line. Okay, so you will see that at time equals to 5 seconds, this graph starts afresh, another oscillation. Okay, it repeats itself after 5 seconds. After 5 seconds, this graph is starting once again. Okay, so the period in this case that they're looking for is 5 seconds. They just want you to see that when this graph gets to 5 seconds, it is basically starting afresh once again. Okay, let's move on. Question 8. Explain why the motion of the engine piston in figure P15.8 is only approximately a simple harmonic motion. Then question B is asking you what must you do to the length of the neglecting rod if you want to make the motion more nearly simple harmonic motion? Okay, so we have already defined simple harmonic motion, and we say that simple harmonic motion obeys the sinusoidal motion. Okay, the motion is supposed to be sinusoidal. Okay, so in order for this piston to have a perfect simple harmonic motion, its motion in the y direction, we'll have to exactly match the y component of the pin on the motor that is moving on a circle. What am I talking about? If you look at this thing that is over here, it is moving at an angle that is different from this one that is here, as this piston is turning left and right. So we can compare this motion of a piston with what we already know for a simple harmonic motion, which is a pendulum. Okay, so a pendulum simple move left and right in a circular manner. But if you look at this piston, it also moves left and right. But then there is this bob over here, which is also moving at its own angles. Okay, so this bob here is what makes this thing to not have a perfect simple harmonic motion, as the question is saying over there. Okay, so B is saying what must you do to the length of the um, neglecting rod if you want to make the motion more nearly harmonic motion. So suppose that for this length over here, suppose that we increase the length of this rod over here. What is going to happen is that the movement of this rod is going to be negligible, which is going to make this piston to be more sinusoidal, okay, in terms of its motion. Basically, this is what this question wanted you to discuss, okay. It wanted you to see that the movement of this bob at the end is going to disturb uh, the perfect movement in terms of getting a sinusoidal curve when drawing the motion for this graph. Okay, but if you make that rod longer, it becomes the bob at the end, its movement, its angle, it becomes negligible. Okay, so we're going to move to question 9. Is the typical up and down motion of a yo-yo periodic motion, assuming no energy is dissipated, um, is it simple harmonic motion? Okay, so the first thing to understand here is what is a yo-yo. So you can quickly search up on YouTube and then you will see the pictures of a yo-yo. It is something like this. Okay, um, not good in drawing. There is a string here and then it is used by children. Okay, and then if someone release it, it just move to the left and then it goes back to the right. Okay, this is a string, so someone will be pulling it and then releasing it and then it will be moving like this. So the question is it a simple harmonic motion? Okay, what we already know the definition of a simple harmonic motion, and then we have already defined what a periodic motion is. So we can ideally see that this yo-yo is in periodic motion because it repeats itself, okay? But then the question is it in simple harmonic motion? It is not in simple harmonic motion because its position and velocity cannot be described by a simple sine or cosine function, okay? Why am I saying that it cannot be defined by a simple sine or cosine function? Let's take for an example of what we already know for a simple harmonic motion. If we have a spring with an object connected, what we said is that when this spring reaches, suppose it is at d equals to 0, we said that the kinetic energy at this point will be 0, okay, when the spring is fully compressed, and then the potential energy will be maximum, okay, will be at its maximum. But then if you have a look at this movement of the yo-yo, it does not reach this point at which the kinetic energy will be 0 and the potential energy will be maximum, because there is also um, a, a vertical movement. Okay, what happens is that not all of its potential energy is converted into translational kinetic energy. Okay, so some of it becomes rotational kinetic energy. So this is why this yo-yo is not a simple harmonic motion. Okay, it is just a periodic motion that is not in simple harmonic motion. Okay, so let's move on to question 10. A highly elastic ball is dropped from a height of 2 meters onto a hard surface. Assume the collision is elastic and no energy is lost to air friction. Show that the ball's motion after it hits the surface is periodic. Okay, so the key words here is the word collision is elastic and no energy is lost to air friction. And then what you can see here is that this elastic ball is being dropped. Okay, so if we drop a ball to the ground and it does not lose its energy, suppose that we dropped it from a distance d above the ground. Usually in real life, if you drop a ball from a distance d, it is gonna go back up, but it won't reach distance d because it's gonna lose its energy. Okay, and in the real life this collision is not elastic, so it wouldn't reach distance d. But then now they're telling you that the collision is elastic and no energy is lost, meaning that this ball will bounce back to a distance d. Okay, that's what they mean when they're saying show that the ball's motion after it hits the surface is periodic. Why are they saying it's periodic? Because if no energy is lost, it will keep on bouncing up and down continuously without stopping or losing energy or decreasing its maximum height. Okay, so basically in this question, no calculation was required, but then they wanted you to just discuss, okay? Because this is required by conservation of energy applied between the first time the ball is at its peak height and the second, okay? But then there's nothing special about the first and second peak position as long as no energy is lost in the collision or to air, as I've already explained here. So let's move on to part B and C of this question. So they're telling you to determine the period of the motion. Okay, so to determine the period of the motion, once again, we will have to discuss the definition of the period in terms of this motion. What we already know is that this ball is going up and down. Okay, no energy is lost. So if this is distance d, this ball is going up and down, going back. So we know that the period of the motion is the time taken for for one oscillation. Okay, so in this case, an oscillation is when this ball goes down and then goes back up. So we need to find the time at which this ball is gonna go down and then go back up. Okay, so this will be our period. And so we are going to find this time using kinematics that we already know from first semester physics and probably grade 12. Okay, so we're going to use the equation that is the displacement is equals to initial velocity multiplied by the time plus half of the acceleration and the time squared. Okay, but then if you can go back and read the equation, you will hear that this ball was dropped. Okay, which means that its initial velocity will be 0. Okay, and then if you can remember that here we are looking for the time, so which means that my reduced equation will be displacement is equal to half acceleration multiplied by time squared. So I'm going to write time as the subject of the formula, which is going to give me square root of 2 delta y divided by the acceleration. Okay, but then what we know about this time is that it is only it's the time for one motion. Suppose, I mean, it will give us this expression here will give us the time taken by the ball for maybe to only go down. Okay, so in order to get the time for the ball for it to go down and then go back up, we have to multiply the time by 2, because we know that it is going to take the same time to go up and then back down. Okay, so to get the the period, we have to multiply this time by 2. Okay, you know the period is the time taken by the ball to go down and then back up. So we multiply this time by 2 here, which is 2 multiplied by the square root of 2 delta y over the acceleration. And we're already given delta y there in the equation. Okay, then we know the acceleration that it is due to gravity. So we just substitute our values over there. Okay, divided by 9.8 for gravity, which is going to give us 1.3 seconds. Okay, so this is our period that we're looking for this question.